Hello and welcome to the lecture on 5.6. Today we're going to talk about harmonic motion. We're going to start with simple harmonic motion and then we're going to move into damped harmonic motion. Now simple harmonic motion is a little bit easier because it's easily modeled with either sinusoidal curve, the sine curve or the cosine curve. Generally how we introduce this topic is with a spring mass system. So suppose that we have this spring here and it's attached to a mass. And what we do is we pull this mass down and then we let it go and it'll oscillate. Right? Now, you have to imagine this in time shots. So if you've ever done this with a mass, a spring and a mass, attach a mass to a spring and then pull it down and let it go and watch it oscillate. If you've ever seen this, take screenshots in your mind of this happening. So let me show you how this looks in practice. Let me go ahead and draw my axes. Let's suppose that we pulled a spring down. We haven't let it go yet, but we pulled the mass all the way down to here. And then we're about to let it go. We haven't let it go yet, but this will be at t equals 0. And we're going to go in intervals. We're going to take snapshots of the spring mass system in intervals of 1/10 of a second. So at every 10th, we take a snapshot of where the spring is, what the position is. So at 0.1, at 1/10, we're right here. This has moved up a little bit. At 2/10, it's moved up even more. Then at 3/10, it reaches about where it's going to be its maximum. At 4/10, the spring mass system is the mass is starting to move down now. 5/10, continuing to move down. 6/10, it's getting really close to its minimum. And then at 7/10, we're going back up a little bit. 8 here, and then 7, 8, 9, going back up. And then at 10, we're going back down a little bit. 10/10 would be at exactly 1 second. I want you to notice this path. It goes up, down, up, down. So it'll keep oscillating back and forth. And if we look at this, we can see that we have a sinusoidal curve. And we get this path, this curve that looks like a sine curve or a cosine curve. Now this is what we mean by simple harmonic motion. It continues to oscillate back and forth forever, really. Again, later on, we'll talk about damped harmonic motion. But for right now, let's go ahead and just think about simple harmonic motion. So simple harmonic motion will always be this oscillation curve, either a sine curve or a cosine curve. Go ahead and define this really quickly. A cycle is one complete vibration of an object. It's one full period of the sine curve or the cosine curve. That's basically what it is. We need to talk about cycles because we're going to mention frequency. And the frequency is measured in cycles per second. Simple harmonic motion model. If the equation describing the displacement of y of an object at time t is y equals a sine omega t, or y equals a cosine omega t, then the object is in simple harmonic motion with amplitude, absolute value of a, period 2 pi over omega, and frequency omega over 2 pi. Notice that the frequency is 1 divided by the period. It's just the reciprocal of the period. But the frequency is measured in cycles per second. That's why we defined what a cycle was. 1 full period per second, per unit of time. That's how frequency is measured. All right, we're going to do quite a few examples here because, they're fun. An alarm in the Millennium Falcon is modeled by the function y equals 40 sine 50 pi t. where y is measured in decibels and t in seconds. A, find the amplitude, period, and frequency. B, sketch the graph of the model. Let's start with A, finding the amplitude, period, and frequency. Again, period and frequency are very closely related, specifically that they are reciprocals of each other. So if I find the period, I know what the frequency is, I just need to take the reciprocal. Go back, we can see that the period is 2 pi over omega, and the frequency is omega over 2 pi, literally just the reciprocal. Now the amplitude is the number in front of the sine or cosine function here. So our amplitude in this case is equal to 40. It would be the absolute value of 40, but since 40 is equal to the absolute value of 40, I'm just going to write 40. Make sure that you have your absolute value bars. This is a very common mistake for students where they forget to put the absolute value bars, and they sometimes write a negative amplitude, which doesn't actually make sense. Period is 2 pi over omega. Now our omega is 50 pi. This will be 2 pi divided by 50 pi. So our period in this case, if we cancel this out, the pi's will cancel. 2 divided by 50 is 1 over 25. So our period is 1 over 25. That's it. And the frequency would be the reciprocal of this, 25. What this means is that our model should have 25 cycles per second because t is measured in seconds. Now let's go ahead and sketch the graph. You should remember how to sketch this. It's sketched the exact same way as, I believe, 5.3 when we went over sketching sine and cosine curves. These numbers don't actually change anything with respect to the graph. The fact that we have an omega here doesn't mean that it's sketched any different than the graphs that we sketched when there was a k here. K just represents this number. In this case, omega represents this number, but it's still the same thing. It's graphed exactly the same. So we can draw our axes. We can write out our period. Period would be here, 1 over 25. That would be one full period of the model. Half of 1 over 25 is 1 over 50. And half of 1 over 50 is 1 over 100. 3 over 100. We have the sine curve, so we start at 0 when t is equal to 0. And then we go up to 40. First point, at the second point, we're at 0. Third point, we go down to negative 40. And then the fifth point is at the 0 because it's the sine curve. So this is what our curve looks like. Now I did want to note here, the amplitude is this distance. This would be the axis over which our function oscillates. Now the amplitude is just the distance from that main axis to the highest or lowest value. So here, this distance is 40, this distance is 40, so we have an amplitude of 40. And that will come up later. I did cover it in a previous video, but I remember covering it very quickly. You also want to make a really quick note here. The main difference between y equals a sine omega t and y equals a cosine omega t is the starting position. Cosine starts at a maximum, sine starts at 0. Now when I say that they start at a maximum or start at 0, I mean that when t is equal to 0, at the starting point, cosine has already reached its maximum value. We saw that here. We reached our maximum value when we were starting. Sine starts at 0, and we see that here. When t is equal to 0, we start at 0. And this we should already know, but it is important to point out because word problems will sometimes use this fact, and they'll write it in this particular way in order to slip a little bit of information by you. Do another example here. An alarm is blaring in the Senate building. The frequency is measured at 5,000 hertz, which is cycles per second. If the amplitude is 60 decibels, find the function that models the sound. Assume the alarm is at its loudest at t equals 0. So this is exactly the piece of information that I'm talking about here. If the alarm is at its loudest at t equals 0, that means that it's at a maximum. So we're going to use cosine and not sine. We also already know what the amplitude is. The amplitude is 60. So A is equal to 60. And we know what the frequency is. Frequency is equal to 5,000. So we need to figure out what omega is. And that's not so bad when we know what the frequency is. If we remember that the frequency is equal to omega divided by 2 pi, and we know that the frequency is 5,000, then we have this. So we just need to solve for omega in this equation. Multiply the 2 pi over, and we get omega is equal to 10,000 pi. Once we have that, we can just write out our function. So y is going to equal 60 cosine 10,000 pi times t. So far we've gone over the models y is equal to a sine omega t and y is equal to a cosine omega t. Now we can generalize this a little bit. Here we have a vertical stretch with our a, our amplitude, and we have a horizontal stretch or compress here with our omega. But what if we needed to shift our sine or cosine function in order to fit a model, some conditions that we have? Well, we can generalize this to be the following functions. Y is equal to a sine omega t minus c plus b. And y is equal to a cosine omega times t minus c plus b. And this will incorporate our vertical shift, b, and our horizontal shift, c, in this case. Now, just as a quick example, just a reminder, we should already be able to do this, but let's go ahead and graph y is equal to a sine omega t minus c plus b. I'm going to assume that all of my values are positive in this case, omega, b, c, and a. Now, with our vertical shift, we have to remember that axis over which we oscillate. Remember, normally sine and cosine oscillate over the x-axis. So when we shift all of our points b units, that axis will shift as well. So at b, again assuming b is positive, we get this axis over which our function is going to oscillate. If we're subtracting c, that means we're shifting this way c units. This would be c here, and this would be c plus 2 pi over omega, whatever the horizontal stretch or compress is. This is b, and then we would have b plus a here, and b minus a. Because remember, our amplitude is how far away we move from that axis that we oscillate over. So if we're oscillating over this axis, the highest point will be a units above that, and the lowest point will be a units below that axis. If we plot this point here, plot this point here, and we have the point in the middle where we cross, we have a maximum here at b plus a, and then we have a minimum here at b minus a. And this will be our sine function, because sine starts at 0. So it starts at the origin, but this point has shifted to the right c units and up b units, so we get to this point. All the other points as well, but just so you know why I'm starting here, because it's sine. So this is what our function looks like. Now, again, we should know how to do this already. This is a problem from 5.3, I believe. Let's do another example here. I had to take a little bit of creative liberty here. Suppose in Jeddah, the day with the most hours of sunlight is 50 days into the year and it has 15 hours of sunlight. The day with the least number of hours of sunlight has 10. Find the function that models how much sunlight Jeddah has. Assume 1 year on the planet is 300 days. So there are a few ways to start this problem. There's a lot of information here. First, let's try to think about our seasons here on planet Earth. In the summer, we have longer days, meaning we have more days of sunlight. In the winter, we have fewer days of sunlight. And that curve is sinusoidal. It should make sense because the Earth is round, even though I'll get a bunch of comments about how it's actually not. So if we measure the hours of sunlight on our y-axis and the days on our x-axis, then we know a bit of information here already. First, at day 50, we have a maximum hours of sunlight, which is 15. We know at day 50 out of 300, we have 15 hours of sunlight. The least hours of sunlight is 10. And that will be over here somewhere. Now, I don't know on what day that happens, but I know that the least hours of sunlight is 10. So I need to figure out a couple of things. First, I want to figure out the axis over which we oscillate. Remember that this is going to be a sine curve. So we're going to have an axis over which we oscillate. And it'll look something like this. Come down, and it'll go back up. Now, we can assume that we actually have a cosine curve instead of a sine curve because we're starting on a maximum here. I'm going to start here. I'm going to start my graph at the maximum value. So I'm going to use the cosine curve instead. So we're going to have a model that looks like this. Y equals cosine omega b minus c plus b. Now this b is going to be our new axis, as we saw in the previous graph. The axis over which we oscillate. Now we know that we have 15 hours of sunlight here, and we have 10 hours of sunlight here. We also know that, we can figure out the amplitude. We can knock out A and B at the same time. First, I need to figure out where this axis lies. And it's going to be exactly between the maximum number of sunlight hours and the minimum number of sunlight hours. So we do 15 plus 10 divided by 2 is going to find the midpoint between these two y values, which will be the new axis over which we oscillate. And this is going to be exactly 12.5. 15 plus 10 is 25. 25 divided by 2 is 12.5. So my b here is 12.5. Now the next thing that I need to figure out is the amplitude. Now the amplitude is going to be the distance from the axis over which we oscillate to the highest value, or the same but the lowest value instead. So here, what we do is 15 minus 12.5 to get 2.5. And this is going to be my amplitude. Now, it should make sense that we actually have to raise up. And we can't have our axis of oscillation on the x-axis. Why? Well, we don't ever have negative hours of sunlight. That doesn't make sense. And if we oscillated over the x-axis, we would dip below the x-axis, which would mean that we would have negative hours of sunlight. So having a shift up actually makes sense. And we get the 12.5, as I said before, as the midpoint between the max and the min value. That should also make sense here. Exactly between b plus a and b minus a. Right. So now we have our amplitude and we have a vertical shift. We need to find our horizontal shift. And that's going to be from t equals 0 to 50. So think of it like this. If the maximum number of sunlight hours occurred on the very first day, or on the 0th day, at t equals 0, then we would have a maximum here. But I'm drawing my curve like this. So I needed to shift over 50 days. So our horizontal shift is going to be 50 days. As the max occurs at day 50, we know that our horizontal shift is 50. And that's going to be C, because C represents our horizontal shift. Now, the last piece of information, of course, is to find our period. Well, a year on the planet is exactly 300 days. So it's going to go from maximum to maximum 300 days later. We'll have the longest day, 50 days into the year, and then the next year, 50 days into the year, again, we'll have a maximum number of hours of sunlight. So 300 is our period. So we just need to figure out what omega is. If you remember, the period is equal to 2 pi divided by omega, and we know that our period is 300. Multiply the omega, divide by 300, and we have that our omega is equal to pi divided by 150. Now, once we have that, we can just write in our model, y is equal to our a value, 2.5, cosine, because we are starting at a maximum. Omega is pi over 150. E minus 50 for our horizontal shift, and our vertical shift is plus 12.5. So if we had to, we would go out, this would be 350, and we would reach a maximum again. So our curve will look something like this. On each day, we can measure how many hours of sunlight we have just by looking at this curve. Now, if we wanted to, we could figure out what day this is. And why don't we do that? Just as an exercise, why don't we figure out what day does the minimum number of hours of sunlight occur on? The maximum occurs on 50. The next maximum would be 300 days later, so at 350. So this would be 150 days after this, because it's exactly between the two maximum values. Our minimum value will be 150 days following the day 50, so it'll be at day 200. We could do the midpoint between these 2 days. 50 plus 350 divided by 2. All right, the next topic I want to talk about is damped harmonic motion. Damped harmonic motion is a little bit more realistic. Whenever we have some sort of resistance that will inevitably make the system come to a stop. Like, for instance, in a spring mass system, it's not technically simple harmonic motion because it doesn't continue to oscillate forever. However, the sun and the number of hours in a day, that is simple harmonic motion because that continues to oscillate forever. Now here, damped harmonic motion just means that the oscillating will come to a stop at some point. Damped harmonic motion will look like this, where we start with a higher amplitude. The amplitude of this function continues to shrink as we move away from the starting point. Now, I will note that the period of this function does not change. The period is not changing. The amplitude is what's changing. Notice that the height over the axis on which we oscillate, the height is reducing each time we oscillate. This is the function of damped harmonic motion. If the equation describing the displacement y of an object at time t is y is equal to k e to the negative ct sine omega t, or y is equal to k e to the negative ct cosine omega t, where c is greater than 0, then the object is in damped harmonic motion. The constant c is called the damping constant, k is the initial amplitude, and 2 pi over omega is, of course, the period. Now, I do want to note a couple of things here, specifically what these variables do. We already know that omega refers to the horizontal stretch, so it's going to refer to the period. 2 pi over omega is exactly the period. Now k is the initial amplitude. Remember, the amplitude decreases over time. So k is just where we started initially. Initially, what was the amplitude of the harmonic motion? And then c is the damping constant. Now, you might not understand what that means. It's basically how fast the reduction in amplitude occurs. So the higher the c value, the faster the harmonic motion will damp to nothing. If it's a very low c value, then you end up with a more along the lines of simple harmonic motion with very small reduction in the amplitude. Now, if we let c equal 0, then we get exactly simple harmonic motion. So that could be a way that you remember it, is if c is 0, you have simple harmonic motion, which means that the larger the c value is, then the faster the harmonic motion will damp. Go ahead and do an example really quickly here. Luke drops a rock in the swamp. Yoda notices the amplitude of a ripple and realizes the amplitude has decreased to a quarter of its previous size over 5 seconds. Find the damping constant. So here, all we're looking for is the value c. So here, because the amplitude, which I'll show shortly, I'll show why this is in a second, but because we're talking about the height of the amplitude, and just the amplitude in itself, I don't really need to use the sine function, or the cosine function, because the maximum value of the amplitude is completely given by this value. And I'll show you that in the graph next. But you'll have to bear with me for a second. So Yoda notices that the amplitude, after 5 seconds, has reduced to a quarter of its original size. So if we ignore this sine omega t, its original size would have fit this model here, this height, this value, whatever it is, for some value t. But he noticed that 5 seconds after that, so 5 seconds after t, it had reduced to 1/4 of its original size, so a quarter of ke to the negative ct. This was its original size. 1/4 of this size would be the size of the amplitude after 5 seconds. That's what this equation is saying. Now all we need to do is solve for t. It's pretty easy because all you do is divide by k, it cancels out. Then we have e to the negative ct minus 5c is equal to 1/4 e to the negative ct. Now if you don't remember, there's a property here, a to the b plus c is equal to a to the b times a to the c. Usually we go from this side to this side because we're adding exponents when we have a similar base. But this time I'm going to do the opposite. I'm going to start with something that looks like this, and I'm going to move to something like looks like this. My base is e, so I end up with e to the negative ct times e to the negative 5c is equal to 1/4 e to the negative ct. Then we can divide by e to the negative ct. This will exclude no t values from the domain because e to the negative ct never actually hits 0, so we would never divide by 0 by canceling these. And then we have e to the negative 5c is equal to 1/4. Take the ln of both sides, and we have negative 5c is equal to ln of 1/4. Divide by negative 5, and we have c is equal to negative 1/5 ln 1/4. Now you might look at this and say, well, look at your c, it's negative. It's not. ln of 1/4 is actually negative as well. So negative 1/5 times a negative value will give me a positive value. We can rewrite this a little bit to say 1/5 ln of 4 if we wanted to, by moving the negative to be a power on the 1/4 by using the log rule. And then you can take the reciprocal of your fraction. So we have 1/5 ln of 4 if you want to look at it like that. But either answer is acceptable in my book. So you get this. Next, I want to show you why we only needed to use ke to the negative ct and we could ignore the sine or cosine values. There's a little bit of a longer argument to it, but it's not really that important. So I'm not going to go over that. Instead, I'm just going to go over graphing damped to harmonic motion. So if we have this, So if we have this function, y equals k e to the negative ct, I'm going to use cosine omega t, because cosine is usually a little bit easier to see with the initial amplitude k. Suppose that we have this and I want to graph it out. So one period of damped harmonic motion will go from here to here. And of course, one period is 2 pi over omega, whatever omega is. Call this one period. Cosine starts at a maximum. This value is k. Now, usually how we do this is we graph e to the negative ct. I kind of have to hand wave the c a little bit, but I can say that this dotted line is y is equal to k e to the negative ct. Now we're using these as guidelines for our max and min values. I'm going to graph the exact same curve, but negative instead. This one would be y is equal to negative k e to the negative ct. Now, I want to note here exactly why we used only this function instead of the sine or the cosine following it. That's because when we graph on this curve, our maximum value will touch the curve. So it will be a point on these curves. So our cosine curve will look like this. It will touch negative k e to the negative ct, and then it'll go back up to 0. Then it'll come back up and touch k e to the negative ct. And if we keep going, we can see that the period actually doesn't change. The amplitude changes, but not the period. Notice that this is 2 pi over omega. The next cycle would be, again, 2 pi over omega, one full period length. But notice that the amplitude is the measurement of this function at whatever t value the maximum occurs at. So here, this t value would be 2 pi over omega. If I plug that in here, that would give me this point because it's on both y equals k e to the negative ct and this function itself. Because cosine would be a maximum, meaning that it reached a value of 1 at this point. So it would be 1 times this function. So this function is always an upper bound on this entire curve, meaning that it plots out the maximum amplitude. All right, I want you to go ahead and try one on the accompanying worksheet. Graph the simple harmonic curve y is equal to 10 sine pi over 2 t. And then graph the damped harmonic curve y is equal to 10 e to the negative t sine pi over 2 t. Now we'll note here your c value is exactly 1. That's pretty large for a c value. Usually the c values that you'll see will be fractional. Do one more example. The string is plucked 4 millimeters above the resting position on the halosket. If the damping constant is 1.1 and the frequency is 260 Hz, find the function that models this scenario. Okay, there's actually a bit more information than you probably immediately see. I want to note that we're plucking it 4 millimeters above its resting position. So it's starting at a maximum. So we're using cosine. We use this function, y equals k e to the negative ct cosine omega t. And again, that's because it's plucked 4 millimeters above its resting position, means it's starting at a maximum value. We also know that c is equal to 1.1. It was given in the problem. That's the damping constant. And we know that the frequency is equal to 260 Hertz. That's the same thing as cycles per second. So again, we know that frequency is also omega over 2 pi. So if we multiply the 2 pi over, we know that omega, using this equation, we can find that omega is equal to 520 pi. So we found omega, and we found c and k is 4 millimeters because it was given in the problem as a maximum value. The function should be this. Y is equal to 4 e to the negative 1.1 t cosine 520 pi times t. The next topic I want to talk about is the difference between phase and horizontal shift. Phase. Any sinusoidal curve can be expressed in the following equivalent forms. Y is equal to a sine at minus b, or y is equal to a sine a t minus b over k. Now these two forms are identical because all we did was factor out the k here, and we get here. So b divided by k would give me the b over k, kt divided by k gives me a t. So the k is factored out. That's the only difference, but they are equivalent. Phase is b. The horizontal shift is b over k. This is the difference between phase and the horizontal shift. When you have your k not factored out, this value is your phase. Now the horizontal shift is after you factored out the k. It is very important to note this. I only created this last section because I think it's very important that you understand that the horizontal shift is found after factoring the k out. This is important. Many people forget to do this. I'm just trying to make sure that y'all don't make the same mistake. All right, that's going to be it for today. I will see you all in the next lecture.